Hello everyone and welcome back. Now, in the previous few videos, we have spent a lot of time understanding second order differential equations. Now what we are going to do in the next few videos is look at higher order equations. So we started with first order equations, spent a long time there. Then we went to second order equations, spent a long time there. We're experts in both of those. And what we're going to do now is we're going to really ramp things up. We are going to go to higher order equations and use all of the knowledge that we've leveraged from these previous equations, carry it over, and sort of expedite our understanding of nth order equations. And that's going to be particularly important in this lecture, where we're going to sort of review a lot of what we've already established for second order equations in the context of nth order linear ordinary differential equations. Now, let's start by writing down exactly what it is that I am interested in. Again, these are nth order, so they're general order. N here could be any number you want. They are linear, and they might be inhomogeneous. So here's what the general form that I'm going to look at is. P0 of t times the nth derivative, y, and then this n in brackets denotes the nth derivative, plus, let's say, P1 of t, and then the n minus first derivative, and so on and so forth until I get to the first derivative, y prime, and then to the original function, y, and this could be equal to some g of t here, okay? So this can be a completely arbitrary. This is linear. You can double check for yourself. All of these p functions, the g function, those don't have to be linear functions of t. What the linearity comes from is the dependent variable y being linear in this equation. Now, just like we have done before, we have an abstract way of writing this. So abstractly, I want to use this operator L again. Remember, operator is just a fancy math term for function of functions. Now, typically what we like to do is we like to divide off that P0 term, right? We've been doing this over and over. We did it with first order equations. We did it with second order equations. We're going to do it here as well. And so that means that I'm going to write my operator L as the nth derivative, the nth derivative, because I divided off the P0. And then I'm going to say here, P1 of t. So I'm going to use little p to denote the fact that this is actually capital P1 divided by P0. Again, you've seen this. Even though it's in a different context, you understand it. All the way over Pn minus 1 of t y prime, and then plus Pn of t y, and I'm going to use little g on the other side here too, just so that we have this g, capital G, being divided by P0 as well. Okay, so what I could do for you now is I could write down a big long theorem that's going to tell you when this thing has solutions. But you can guess it. I am willing to bet that you can guess it, right? Because we've seen it with first order equations. We've seen it with second order equations. What's it going to say? Well, if P1, P2, all the way to Pn are continuous on some interval, and so is G, and that interval contains your initial value T0, then you've got a unique solution to this thing. And that unique solution exists on that entire interval where you have continuity. So I'm not going to write that theorem because we already know what it's going to say. We've seen it before. I'm not going to bore you to tears with this theorem. What I do want to remind you of is the principle of superposition. So the principle of superposition. Now, the principle of superposition, remember, told us for second order equations that if I took two solutions, then I can add them together and get another solution. In fact, I could take a linear combination of those and get another solution. Well, in this case, I get exactly the same thing, right? So let's say let y1 all the way to yn be solutions of Ly equal to 0. Again, I'm taking a homogeneous equation. That's the only way that this can work. And then, well then, so is y of t equal to, say, a multiple of c1 plus a multiple of y2 plus a multiple of every single other one of them. All right, so I can add up solutions and I still get a solution to this thing. Okay, so the principle of superposition tells us that we can add these solutions together and still get solutions, okay? And remember, the name of the game when it comes to linear systems or linear differential equations is tuning C1, C2, and all, in this case, all the way up to Cn, so that you can fit the initial conditions. So, of course, this is an nth order differential equation. That means it's going to need n differential equation or initial conditions going all the way down to the first, or the n minus first derivative. And so, if we put all this together, if this is what our solution is, so we identified n different solutions, we want to sum them up, and we want to try and satisfy the initial conditions. Again, the same thing that we've been doing over and over and over again. Well, here we're going to get C1, y1 of t naught, plus C2, y2 of t naught, blah, 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 Cn, yn of t naught, is equal to, now this is going to be the initial value that you're given, y naught. Keep it going. Okay, let's do it for the derivatives. Hopefully you can see where I'm going, right? So C2, y2 prime of t naught plus Cn, yn prime of t naught is equal to y naught prime. And I'm going to switch colors here because my marker is not doing well. And then I'm going to keep going, so then I have the n minus first derivative. Look at that. That shows up so nice. Sorry, this is y1 t naught plus c2 y2 to the n minus first derivative at t naught. Oh, yeah. So we know what's going on, right? Maybe we can almost smell it coming up. Try and guess what's going to happen next. Okay, so now I've got my big system of equations. In fact, this is a system of linear equations, and that means that I can turn it into a matrix. So let's write the whole thing as a matrix. I apologize if some of this is a little difficult to see. Hopefully now with this marker, it'll be nicer. But now I've got big old matrix here. y1 of t naught, y1 prime of t naught, all the way down to yn minus 1 t naught. And let me skip writing y2. Let me just go all the way over, just because it's a lot to write. But it's all of the solutions evaluated at t naught in the first row, all of their derivatives evaluated at t naught in the second row, and then continuing on until you get to the n minus first derivatives, again evaluated at t naught in the last row here. This is, again, C1, C2, Cn, and you want this thing equal to y naught prime, all the way down to y n minus 1 naught. So you have initial conditions on the state itself, its derivative, its next derivative, all the way down until it's n minus first derivatives. Again, if n is equal to 2, you've seen this before, right? The state itself and its first derivative. If n is equal to 3, then it's the state, its derivative, and its second derivative. Okay, so that's, I don't want you to get too intimidated by the abstraction here. Again, this is sort of just what we've seen, just, taking it up a notch, right? Sort of inductively. But this thing right here is an n by n matrix. In fact, when n is equal to 2, that is the matrix that we use to define the Wronskian. So what was it that I wanted you to try and guess was coming next? It was the Wronskian, all right? So again, we have the same idea. So let's say the Wronskian. So let W, and remember we're going to use this notation. Remember, it depends on t, be the determinant of the n by n matrix. And I'm just going to use an arrow. It's that n by n matrix, right? So it's a lot more writing in this lecture than it is actually really thinking, right? It's just an extrapolation lecture. And I'm using this to really sort of formalize things that we might already understand sort of intuitively. So the Wronskian is the determinant of this thing. Why do I care about the determinant of this thing? Determinant tells me if this thing is invertible. As long as the Wronskian is not 0, this thing is invertible. And if that thing is invertible, there's a unique solution for C1, C2, all the way to Cn. What does that mean? Well, remember what it meant for the second order equations. It means I can satisfy the initial value problem, right? So my set of solutions, y1, y2, y3, all the way to yn, that's a good set. In fact, it's such a good set that we have a proper way of referring to it. And that proper way is a fundamental set of solutions. Remember, we saw this before when we talked about two-dimensional or second order equations. Now we're just stepping it up to nth equations. And now let's think about this in terms of a linear algebra problem. Essentially what this is telling us is that our solutions y1, y2, y3, y to the n are all linearly independent, right? At the value t0, these things are linearly independent. If the Wronskian is 0 or is not 0 for every single value of t that it's defined for, that gives us a linear independence relation, right? So you might have to go back to your linear algebra notes for this, but this is just a way of talking about functions as linearly independent. Okay, with the Wronskian, we talked about how that tells us if a set of functions is linearly independent. Now, this is probably the newest aspect of what we're discussing in this lecture, so let's really sort of dig deep on that. So let's look at an example. We're going to talk about linear independence of a set of functions. So we can ask ourselves, are f1 of t equal to, let's say, 1, f2 of t equal to t, and f3 of t equal to t squared, linearly independent? Okay, well, let's take a look at what this means. Remember, for a linear independence, you need to take a linear combination. So you say you have a linear combination. So remember, we're going to use k's here. So k1 f1 of t plus k2 f2 plus k3 f3 is equal to 0. Now, when you did this with vectors, you needed to show that the only way to satisfy this thing is if k1, k2, and k3 are all going to be 0. If there's a non-zero solution to this thing, then these things are linearly dependent. So we're going to actually do exactly the same thing here, except now I get k1 times f1, that's 1, plus k2 times f2, which is t, plus k3 times f3, which is t squared. Now this has to hold for every single t. So this is for all t and r. Every single value of t, this has to hold for. And so the question is there a non-trivial or are there non-zero values of k that make this true for every single value of t? Or is it the case that these things are linearly independent? That means that they span different spaces. And so therefore, these functions are sort of distinct, right? They all sort of move in different directions if you think of them abstractly belonging to a vector space of functions instead of vectors this time. Okay, so we don't have to get too into the weeds, but one way that we can show that these things are linearly independent is we can check at different values of t, because k1, k2, and k3 cannot depend on t. They have to be the same no matter what the value of t is. So let's look at this. So at t equal to 0, well, this gives me k1 is equal to 0, right? So k1 plus 0 k2 plus 0 k3 is equal to 0. Similarly, at t equal to 1, this gives me k1 plus k2 plus k3 is equal to 0. And I'm going to pick 3 different t values. I'm going to use -1 now. So I get k1 minus k2 plus k3 is equal to 0. So now, I mean, if these things are linearly dependent, I should be able to find values for k here. And they have to hold for all of these t values, right? Well, clearly this gives me k1 is equal to 0. Okay, so f1 is not contributing to this linear combination, right? The only way this is going to be true for every single value of t is if k1 is equal to 0. But that gets rid of everything here, and I get k1 plus k3 is equal to 0, and minus k2 plus k3 is equal to 0. Both of these give you that k2 and k3 have to be equal to 0. So let's step back here. Let's zoom out. Let's see what it is that I really said. I said that if k1f1 plus k2f2 plus k3f3 is equal to 0, this is the equation you're going to check for linear independence. If that's going to be true for every single t, you told me, you said that's true for every t. I said, okay, then it's got to be true for t equal to 0. But that's kind of weird because that gives me k1 is equal to 0. Whatever, maybe that's the case. I said, okay, if it's going to be true for every single t, I'm going to try for t equal to 1. Okay, then I get this equation. That's fine, it's an equation. And I said, well, you know, if it's going to be true for every single t, it also has to be true for t equal to -1. But for t equal to 1 and t equal to -1, I get that k2 and k3 have to be equal to 0. So what have I done? I have shown you that the only way to satisfy this linear combination is if k1, k2, and k3 are all equal to 0. Now, why is that important? Because that tells me linear independence. So therefore, f1, f2, and f3 are linearly independent. Right? So that is exactly what the Wronskian would tell you. You can take these equations and you can put them, or these functions, you can put them into the Wronskian. You can compute the Wronskian of them, and you can also see that the Wronskian is never 0 for all values of t. And that, again, is going to give you that these things are linearly independent. So 2 different ways to tackle this. You can use the Wronskian, but I wanted to use the sort of original way here so that you can really see, you know, what's going on under the hood. Let's take a look at another example, because you might be tempted to say, well, maybe just like all functions are linearly independent. So let's say our f1 equal to 1, f2 equal to 2 plus t, f3 equal to 3 minus t squared, and f4 equal to 4t plus t to the 4, linearly independent? Well, again, let's take a linear combination, right? So I gave you 4 functions. Sorry, this should be a t squared, pardon me. I've got 4 functions. Now let's do linear combination time. K1 F1 plus K2 F2 plus K3 F3 plus K4 F4. Well, this isn't too bad. Essentially, I'm going to get a quadratic polynomial with K1, K2, K3, and K4 as coefficients here. So let me collect all the like terms first. I get K1 plus 2K2 plus 3K3 plus K2 plus 4K4 T, and then plus minus K3 plus K4 T squared. And remember, I want this thing equal to 0, okay? Now, this is a polynomial equation. If it's going to be equal to 0, it's essentially going to be what I just showed in the previous equation, right? Because this is constant, plus t term, plus t squared term. Now, the only way that this thing can be equal to 0 from what I just showed in the previous example is we need, well, what do we need? We need the constant term equal to 0, so K1 plus 2K2 plus 3K3 is equal to 0. We need the t term equal to 0, so that's K2 plus 4K4 is equal to 0. And we need the t squared term, minus K3 plus K4 is equal to 0. Now let's take a hard look at this. There are 4 unknowns, K1, K2, K3, and K4. There are only 3 equations. So what does that tell us? Well, there are more variables. So let's take a note here. 4 variables, but only 3 equations. Now, from our linear algebra, this tells us that there has to be a non-trivial null space to this thing. There's a non-trivial kernel. But that means that there is a non-trivial solution. So that means that there exists non-trivial solution, which is not all K1, K2, K3, K4 equal to 0, right? There's some combination of these things, which you can easily solve for if you'd like. There are infinitely many solutions. It's a one-dimensional null space in this case, or kernel, whichever way you want to think of it. So for example, you could take K1 equal to 5, K2 equal to minus 4, K3 equal to 1, and K4 equal to 1. What does that tell you? That there is non-zero values of K that make this thing equal to 0 for every single T, right? Because the first equation gave you no constant term. Second equation gave you no T term. The third equation gave you no T squared term. So this disappeared, and this disappeared. That gives you all of this is equal to 0 for all T. That tells you that you have a linearly dependent set of solutions, right? Exactly the same thing that we see with vectors. It's just that we have a time dependence in here, or T dependence. We have an independent variable. I always think of T as time, but again, we can sort of abstract this. It could just be, any independent variable we would like. Okay, so what did we show? Well, I sort of gave you a quick and dirty introduction to nth order linear equations. I told you when you can expect solutions, and you probably could have guessed it. I told you when they are going to satisfy the initial values for regardless of the initial values that are given to you. That comes from the Wronskian again, except now we're stuck taking a determinant of a much larger matrix, right? It's an n by n matrix coming from the fact that an nth order equation has n solutions, right? So we're sort of pushing all of our knowledge that we have so far. First order equations have 1 solution. Second order equations have 2 solutions. nth order equations have n solutions, right? We're sort of just, we're doing a little bit of mathematical induction here, taking what we already know and pushing it forward. Really what we focused on is looking at what it means for something to be linearly independent. Now that is also captured by the Wronskian. It's entirely up to you. You could do it this way, or you could do it with the Wronskian. Either way works. They actually are completely equivalent, and that's just a fact from linear algebra. So you might have to remember a little bit of linear algebra for this, but it's in there somewhere, hopefully, and hopefully this isn't too bad for you.